Take a slow breath in and let it out gently. There is nowhere you need to go, nothing you need to do. For the next while, you can simply listen and let your mind drift outward, far beyond the surface of Earth, into the true scale of the universe. When we hear the word space, we often imagine stars scattered across darkness. But space is not just emptiness. It is distance. It is time. It is scale far beyond everyday experience. To understand the universe, we must first understand how vast it truly is. So let us begin gently. Right here, on Earth. The Earth feels large to us. It takes hours to cross a continent, days to cross an ocean. But from space, Earth is a small blue sphere, less than 13,000 kilometers wide, floating quietly in the dark. Orbiting Earth is the Moon. Even the Moon, our closest neighbor, is nearly 400,000 kilometers away. Light, the fastest thing in the universe, takes over 1 second to travel from the Moon to Earth. Already, we are stepping beyond intuition. Now let us move outward, slowly. Earth orbits the Sun at a distance of about 150 million kilometers. This distance is called 1 astronomical unit. Light from the Sun takes about 8 minutes to reach Earth. When you feel sunlight on your skin, you are feeling energy that began its journey 8 minutes earlier in the core of a star. The Sun itself is immense. More than 1 million Earths could fit inside it. And yet, the Sun is an average star, not especially large, not especially small, just one quiet star in a galaxy filled with hundreds of billions more. Now imagine drifting past the outer planets, past Jupiter, past Saturn, past Uranus and Neptune. Beyond them lies the Kuiper Belt, a vast region of icy bodies and ancient debris left over from the formation of the solar system. Even farther out lies the Oort cloud, a distant spherical halo of material that may extend halfway to the nearest stars. At this distance, the Sun is no longer a bright disk. It is just another point of light, among many, and still, we have not left our local neighborhood. The nearest star system, Proxima Centauri, is over 4 light-years away. A light-year is the distance light travels in 1 year, nearly 10 trillion kilometers. To reach Proxima Centauri, with today's technology, would take tens of thousands of years. Between stars, there is vast emptiness. Stars are not clustered tightly together. They are islands, separated by oceans of space. This separation is what keeps the galaxy calm. Collisions are rare. Chaos is limited. Now imagine pulling back further until individual stars blur together into a soft glowing band. This is the Milky Way galaxy. Our galaxy is a vast rotating disk, about 100,000 light-years across. It contains hundreds of billions of stars, and perhaps trillions of planets. At its center lies a supermassive black hole called Sagittarius A. It is 4 million times the mass of our Sun, and yet, even this enormous object orbits quietly, governed by gravity, balanced within the galaxy. The Milky Way is not alone. It is part of a small family called the Local Group. This group includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller galaxies. Andromeda itself is larger than the Milky Way. It lies about 2.5 million light-years away. The light you see from Andromeda tonight began its journey before modern humans existed. Galaxies are not static. They move. The Milky Way and Andromeda are slowly drifting toward each other. In about 4 billion years, they will merge, not in a violent crash, but in a slow, graceful dance lasting hundreds of millions of years. Stars will mostly pass by one another untouched. Space is simply too vast for chaos to dominate. Now pull back further still. Galaxies gather into clusters. Clusters gather into superclusters. These structures trace vast filaments, stretching across the universe, forming what we call the cosmic web. Between these filaments are enormous voids, regions of space, with very few galaxies at all. These voids are not empty. They are simply quiet. The universe, at its largest scales, is structured like foam, bubbles of emptiness, surrounded by threads of matter. This pattern did not form randomly. It emerged slowly from tiny variations in the density of the early universe. Gravity amplified these variations over billions of years. Nothing rushed, nothing forced. Now consider this. The universe is about 13.8 billion years old, but because space itself has been expanding, the observable universe is far larger than 13.8 billion light-years. In every direction, we can see about 46 billion light-years. That means the observable universe is about 93 billion light-years across. This is not the size of the entire universe. It is only the part from which light has had time to reach us. Beyond this cosmic horizon, the universe likely continues, with more galaxies, more stars, more space, but their light will never reach Earth. Not because of a barrier, but because space itself expands faster than light can cross it. There is no edge, no wall, no boundary, just a limit to observation. This is one of the most calming truths in cosmology. The universe does not end. It simply extends beyond what we can see. And you are not small within it. You are part of it. Every atom in your body was forged in ancient stars. Every breath you take is connected to processes that began billions of years ago. The universe is not separate from you. It is expressing itself through you, and it is in no hurry. As we move deeper into the true scale of the universe, we begin to encounter something unseen, something that does not glow, does not reflect light, and does not reveal itself directly. This is dark matter. Dark matter makes up about 27% of the universe. It cannot be seen with telescopes, but its presence is undeniable. Galaxies rotate faster than visible matter alone can explain. Clusters of galaxies are held together by more gravity than we can account for. Gravitational lensing, the bending of light, reveals invisible mass, curving space-time. Dark matter acts like a cosmic framework. It forms vast halos around galaxies, providing the gravitational structure upon which visible matter settles. Without dark matter, galaxies like the Milky Way would likely never have formed. The universe would be smoother, emptier, less structured. Dark matter does not rush. It drifts slowly, responding only to gravity. It does not interact with light, which means it does not heat up, does not cool down, and does not collide. It simply exists, quietly shaping the cosmos. And then there is dark energy. Dark energy makes up about 68% of the universe. It is even more mysterious. Dark energy is not a force in the traditional sense. It is a property of space itself. As space expands, dark energy becomes more dominant. It pushes galaxies apart, not by motion, but by stretching the fabric of space-time. Astronomers discovered that the expansion of the universe is accelerating. This was unexpected. Gravity should slow expansion. But something else is at work. Dark energy does not clump. It does not form structures. It is smooth, even, and constant. It fills all of space. This means that as time passes, the universe becomes quieter. Galaxies drift farther apart. Interactions become rarer. The universe slowly settles into isolation. This is not destruction, it is dispersal. Now let us return to the early universe. In the beginning, the universe was incredibly hot and dense. Space itself was compressed. Temperatures were so high that atoms could not exist. Particles formed and vanished rapidly. Then, as the universe expanded, it cooled. Protons and neutrons formed. Later, atoms formed. Light was finally able to travel freely. This moment left behind the cosmic microwave background. This faint glow still fills the universe today. It is nearly uniform, but not perfectly. Tiny fluctuations in temperature and density became the seeds of all cosmic structure. Every galaxy, every star, every planet traces its origin to these tiny variations. The universe did not need guidance. It followed physical laws. Now consider inflation. Inflation is a theory that describes a brief moment just after the Big Bang. During inflation, space expanded exponentially fast, faster than the speed of light. This expansion smoothed out irregularities, explaining why the universe appears so uniform in all directions. Inflation may also explain why the universe is so large, much larger than we can observe. If inflation occurred, then the universe beyond our horizon may be unimaginably vast, possibly infinite. In such a universe, what we see is only a tiny patch of a much greater whole. This idea does not diminish us. It reminds us that the universe is generous. It contains far more than we will ever need. Now let us return to the Milky Way. Our galaxy is about 13 billion years old. It formed gradually from smaller galaxies merging. Stars continue to form today in spiral arms where gas and dust gather. The Milky Way is not static. It breathes. Stars are born. Stars die. Material recycles. This slow rhythm has continued for billions of years. Our sun formed about 4.5 billion years ago. Earth formed shortly after. Life appeared relatively quickly. This suggests that when conditions are right, complexity arises naturally. Life may be common, but distance is vast. Civilizations, if they exist elsewhere, are separated by immense time and space. This distance creates silence. Not emptiness, but quiet. Now imagine the scale of time again. The universe is old, but still young, compared to its future. Stars like the sun will shine for trillions of years. Red dwarf stars, the most common stars, burn slowly. Some will shine for 10 trillion years or more. The universe is not winding down. It is just beginning its long, quiet phase. In the far future, galaxies outside our local group will disappear beyond the horizon. Observers in the distant future may see a smaller universe, not because it shrank, but because expansion carried everything away. Knowledge itself is tied to time. What we can know depends on when we exist. You exist now at a moment when the universe is rich with structure, light, and complexity. This is a fortunate time, a calm time, a balanced time. And as you listen now, you can feel that balance. There is space to breathe. There is time to rest. Now let us focus more closely on the galaxy we live in, the Milky Way. The Milky Way is a barred spiral galaxy. This means it has a central bar-shaped structure made of stars, with spiral arms extending outward. Our galaxy is about 100,000 light-years across and several thousand light-years thick. It contains an estimated 100 to 400 billion stars. Most of these stars are smaller and dimmer than our sun. Red dwarf stars are the most common type in the Milky Way. They burn fuel slowly and can shine for trillions of years. This makes them stable, long-lived objects and potential hosts for planetary systems. The Milky Way is structured into several main parts. At the center lies the galactic core, a dense region filled with stars, gas, and dust. At the very center of this core is a supermassive black hole called Sagittarius, a star. It has a mass about 4 million times that of the Sun. Despite its size, this black hole does not consume the galaxy. It remains stable, its gravity balancing the motion of surrounding stars. Stars near the center orbit this black hole at incredible speeds, providing direct evidence of its existence. Extending outward from the center are the spiral arms. These arms are regions where gas and dust are concentrated. They are sites of active star formation. Our solar system is located in a small spiral arm called the Orion Arm, about 26,000 light-years from the galactic center. This position is relatively calm. We are far enough from the dense core to avoid frequent stellar interactions, and far from the outer edge, where stars are sparse. This stable location has allowed the solar system to remain relatively undisturbed for billions of years. The Milky Way is surrounded by a halo of stars, globular clusters, and dark matter. Globular clusters are dense groups of ancient stars, some of the oldest objects in the galaxy. Many formed over 12 billion years ago. They orbit the Milky Way in large, elongated paths. The dark matter halo extends far beyond the visible galaxy. It contains most of the Milky Way's mass and plays a crucial role in holding the galaxy together. Without dark matter, the Milky Way would rotate too quickly and tear itself apart. The galaxy rotates once every 200 to 250 million years. This period is called a galactic year. The Sun has completed about 20 such orbits since it formed. Throughout its history, the Milky Way has grown by absorbing smaller galaxies. Some of these mergers are still visible today as streams of stars stretching across the sky. This process continues. The Milky Way is currently interacting with nearby dwarf galaxies. In the distant future, it will merge with the Andromeda Galaxy. This event will reshape both galaxies, forming a larger elliptical galaxy. Despite the scale of this collision, individual stars are unlikely to collide. The distances between stars are simply too great. Galactic evolution happens slowly, over billions of years. The Milky Way is not static. It is dynamic, constantly changing, yet remarkably stable. It is one galaxy among hundreds of billions in the observable universe, and yet it is the only one we call home. Understanding the Milky Way helps us understand how galaxies form, how stars are born, and how planetary systems develop. It places our solar system within a much larger structure and gives context to our place in the universe. When we study the Milky Way, we are not just studying distant stars, we are studying our own cosmic environment. And with that understanding, we reach the end of this journey through scale, structure, and the vastness of the universe. Everything we have discussed, from planets to galaxies to cosmic expansion, fits together as part of a single connected system. That system is the universe, and we are within it.